Okay. This talk, unfortunately, is not as elaborate as I wanted it to be, but we'll have some fun with this. So, we know how trees are built, different methods. Now we'll start getting into applications of phylogenies. In fact, after this, tomorrow I was supposed to talk about applications of molecular phylogenetics. What I'm going to do is try and squeeze it in today so that we have more time for computer lab tomorrow. Okay. Okay. How many of you have heard this term phylogenetic diversity? Show of hands. Oh, not many. I would okay. Not even half the number. So, hey, but wait a minute. Before, okay, we'll do it after this. I wanted a round of introduction. I completely forgot about it. We are already on day 3, but we'll do it after this, or maybe in the afternoon. Okay, so what I'm going to talk about is a sort of a collaboration of 4 of us, and actually Divya has done a lot more work. There's another interesting application of phylogenetics, and that is with respect to calculating endemism. There's something called phylogenetic endemism. I actually wanted to incorporate that also in this talk, but lack of time, I could not. So, but we'll just stick with phylogenetic diversity. Okay. Now, when it comes to characterizing biodiversity, right? We usually count number of species, right? So, diversity. One of the diversity indices is species richness. You just count up the number of species in a particular area, and you do that for multiple areas, and the area with the highest number of species has the highest diversity. One can also look at evenness. I hope you guys know the term evenness, right? What are some of the diversity indices that incorporate evenness? Simpson's diversity indices and this Shannon's, yeah. So where you also look at numbers of each species, right? But all these measures tell you how many different species there are and how what is their distribution in terms of evenness, but they don't tell you how different those species are from each other. Okay, so that is where it becomes very important to bring in phylogenetics, right? So look at this example here. There are 2 areas, very simple example. Both the areas have same number of species, so they have the same amount of diversity. One might argue species richness is the same, but I would argue that one of the areas has a higher diversity than the other. What am I thinking? Anyone? A is more. Why? Yeah. So they are very phylogenetically very different. So there's a primate here. There is a canid. There is an ungulate, and there is that's a phyllid, and that's a canid, right? Whereas here they're all canids and ungulates. That's it, right? So phylogenetically these are more distantly related. So in fact there's a lot more diversity here. So when we build a phylogenetic tree, there's more deep divergence here. So basically biodiversity should also encompass evolutionary history. Right, and that's called phylogenetic diversity. Now, people have noted this issue. I mean, it's not like with the advent of phylogenetics, all of a sudden people said, "Oh, this is a problem. We should include more information when it comes to determining diversity. So in the past, what people have done, for example, they have said, let's look at diversity at a higher taxonomic level to incorporate more information in your calculation of diversity. For example, area A has 3 different orders of mammals. This has only 2 orders of mammals. So, this is going to cover the information. You don't really need phylogenetic information, right? Traditional classification will do the job. But the problem is, there's a lot of taxonomic ambiguity in traditional taxonomy, right? In many cases, taxonomic groups are not monophyletic, and evolutionary history encompassed by various groups might be very different. What do I mean by that? If you compare class Insecta and class Mammalia, the hierarchy is at the class level. But if you look at the actual evolutionary history and look at how old these lineages are, insects are much older. The mammalian radiation, so mammals were there in Cretaceous, probably they evolved in the Cretaceous. Whereas, so mammals are, I don't know, maybe 140 million years, the earliest mammal, or maybe a little later than that. But insects are, I don't know, maybe the Devonian or something, right? So it's probably more like 300 or 400 million years, right? So if you take 2 distantly related insects, its common ancestor goes way back, whereas 2 distantly related mammals, it's much more recent. So this hierarchy, class, is not comparable across taxonomic groups, right? So higher level taxonomy does not give you the complete picture. So we have to use phylogenetic tools. So anyway, so what is PD? What is phylogenetic diversity? It's a measure of diversity that takes into consideration evolutionary history of species in an area by incorporating the degree of relatedness among them in calculating diversity, right? And it's very simple. It was originally proposed by Wainwright, but it's this guy Faith who sort of popularized it. It is basically the sum of branch lengths of an phylogenetic tree of species from an area. Okay, what do I mean by that? Here's an example. You have 4 areas. All of them have the same number of species. So that bar is basically, what are the species in that area. For example, area 1 has A, B, and C, and so on. So which among these 4 areas has the highest phylogenetic diversity? Yeah, 3 has the highest. 4, no. Yeah. Now the question is, why does 3 have the highest phylogenetic diversity, right? So sum of branch lengths of all the species in that area gives you the phylogenetic diversity. So area 1 has these 3 species. You sum up the branch lengths all the way to the root. So when you do that, you get a PD of 8. This is area 3, distantly related species. So the sum of branch length here is very high, right? And these other areas have lower PD. So this has the highest PD, okay? Yeah, so that area 3 has the highest PD. Okay, so to illustrate this, we did a little project. In fact, you guys can all think of projects like this. I had an intern in the lab. Her name was Shrishti, and she wanted to spend like a couple of months, do a little project, and she wanted to know more about phylogenetics. So I was thinking, what shall I ask her to do? And we came up with this fun project, and that was, let us pick some wildlife sanctuaries in India, right? And then find out what is the mammalian diversity in those sanctuaries. and then also let's calculate PD. Now mammals are well studied, so there's a lot of genetic data already available there. And the information about mammalian diversity is also out there. So, we can get reliable information. So we selected a whole bunch of national parks, so Dachigam and Corbett from the north, Gir and Ranthambore from the west, Bandipur and Annamalai from the south, Khana from central India, Namdafa and Kaziranga from the east. And we excluded rodents and bats and small carnivores because for these groups the information is not very good. In fact, rodents, there's also, I'm sure, a lot of diversity is still unreported, maybe for bats also. So these three groups were excluded, all other species were included, right? So we said, okay, let's just, so a total of 51 mammals were recorded in these, I don't know how many parks was that, 11 or 12? 9, huh? Okay. And then we built a cytochrome B phylogeny for all these 51 species. And then we calculated PD according to Fate's method of calculating PD. So here's the phylogeny. We didn't have to generate any data. All this data was already in GenBank. So basically, when you calculate PD, this is what we got. Okay, so this is species richness. Now, species richness here has been arranged from lowest species, the sanctuaries have been arranged from the lowest species richness to the highest. And then this is the corresponding PD. So, one thing that is apparent from this exercise, in fact, better illustrated here, with increase in species richness, PD increases. And there's a nice linear relationship. And people have shown this in the past. So, why do we need PD then? Right? And this makes sense because as you add more branches to a phylogeny, PD will increase because branch length is increasing. Okay. However, if you see, there are some outliers, that are away from this line, and that's when it starts to get interesting. Okay, so here's the same data. This bar, I believe, is species richness, the green bar, and the blue bar is PD, and the PD values are here, species richness values are here. Okay. Again, they are rank ordered from lowest species richness to the highest species richness. Okay. Now, what do you see anything interesting here? What's so special about Corbett? Huh? Okay. Yeah. That's right. And anything else? So you're saying here PD has gone down. Even though Corbett has more number of species than Annamalai, it has lower PD. Good point. Yeah. Anything else? That's an interesting observation. Yeah. I'm not sure if it is true in all cases, but that is an interesting observation. look at this. These two sanctuaries have the same species richness, but one of them has a higher PD. Huh? Sorry?
Also in Corbett and
Uh-huh.
Kaziranga, species which is
Yeah, and Kaziranga has more, yeah. So you are seeing all kinds of combinations. Same species richness, different PD. One area has lower species richness but higher PD than the other area, right? Yeah, so you know, clearly just species richness is not a good idea, right? Because you have many cases where, you know, same species richness can give you different PD simply because the compositions are different of species. So one has to correct for species richness while calculating PD. Otherwise, you'll get that linear relationship, and then you'll have to actually look at it in this fashion, right? Now, if you correct for species richness, and how do we do this? This is, you basically do pairwise genetic distance between all species in your area, and you divide that by number of comparisons. Okay? So you cannot just take PD and directly divide it by number of species. You know, that's not the right way to do it. That's a little problematic. So instead, what you have to actually do is recalculate PD by calculating pairwise genetic distance, all possible pairwise genetic distance, and divide that by number of comparisons, right? So that controls for species richness. And when you do that, you see something very remarkable, right? Again, this is according to species richness, going from low to high. Okay, look at the high end. Corbett has actually very low PD, right? Whereas some of these places have very high PD, even though species richness is low, right? And Kaziranga and Namdafa are comparable, and look at Anamale, very high, right? So then you can begin to ask the question, what are the species that are contributing to high PD in some of these places, right? Why do you think Ranthambore has low PD? It might have closely related species. So at this end of the phylogeny of the distribution, you will realize that none of these sanctuaries have elephants. Okay, and if you look at the phylogeny, where are the elephants? I believe that is elephant. Is it better here? Yeah, Maximus, yes. So it is completely separate from everything else. So it adds a huge branch, okay? In fact, there is a drop here in Kana also. As far as I know, Kana does not have elephants. Am I right? Anyone? Kana does not have elephants, right? So, you know, it makes a... Corbett has elephants. But I think Corbett lacks some species that is found in Anamale, which is, you know, inflating the... Kana. Central India. No, it does not. I'm pretty sure Kana does not have elephants.
She is talking about Ranthambore.
Ranthambore does not have elephants.
We have safari for it.
No, I'm talking about wild elephants. No, don't include domesticated animals. While doing PD calculations, be very careful, no exotics. Your PD will go out of whack, right? Plant richness, like people are on campus, if you start looking at species richness when it comes to plants, and then calculate PD and you include species like eucalyptus and, the PD will be more than, virgin evergreen forests of Western Ghats, Yeah, so just keep that in mind. So, what species you're including is very important. Even when you're calculating species richness, you cannot really include those species, right? So there's something about Corbett that I remember. There's another group, mammals. So I think this might be a loris or something, absence of loris, or I don't know. Are lorises found in? I don't think so. But in South India we had loris, and then in Northeast we have got them. You have slow loris there. In South we have slender loris, right? So you can actually, drop certain species and see, which are the species that are contributing to this high PD. Right? And it starts to get really interesting because then you're like, maybe we have to prioritize some of these species because you want to conserve the evolutionary history of that area, right? Okay, so, we have looked at all these scenarios. Typically this is what we would like to see, species richness increases, PD increases, but often that is not the case. You have same species richness, one area has more PD than the other area. So species area A are species in area A are phylogenetically diverse. Therefore, area A has higher diversity than B, because same number of species, one area has higher phylogenetic diversity. This is an interesting situation that we also looked at, where area A has higher species richness than B, but B has higher phylogenetic diversity, right? So this is basically, species in area A are phylogenetically very similar. So there are many probably redundant species there, where they're very closely related species. So once again, area B deserves higher conservation priority. And then you have a situation like this, where area A has more species richness than B, whereas the PD is almost the same. Okay, so this means species in area B are phylogenetically diverse, right? And so on. So there are numerous ways of looking at it, and you can come up with areas to prioritize based on phylogenetic diversity and species richness. You should use both of them together. But before that, I should mention that this is a very poor, just 1 minute, very poor comparison in the sense that these sanctuaries should not be compared. Okay, so this was just an exercise. In fact, we have published this in Journal of Bombay Natural History Society, and at the end we say, hey, we're not saying, Namdafa is the most important sanctuary and let's forget about the rest. This is a horrible comparison in the sense that each of these sanctuaries are in a very, very different ecological zone, right? So when you are comparing PDs, it should be areas that are actually comparable in the sense same habitat, same biogeographic zone, and then you are looking at multiple areas within that zone, then it's okay. Yeah, but this was just to illustrate the point that PDs can be very different. Someone had you had a question.
Mine was something related.
Okay. Yeah.
With the size, we don't consider the size because it's relative comparison. The size of
Oh, size of the sanctuary, yeah, because there is a correlation between area and number of species, right? No, that is not included here, but does not matter. You know, end of the day, we just want to see species richness and PD. Yeah. Okay, so just to wrap this up, species richness in conjunction with PD should be used, and information regarding evolutionary relationship is very important. Traditional morphology-based classification cannot be used as a surrogate to determine how different species are, because of, you know, I talked about how classes in two different groups can be of very different ages. This approach can also be used to identify what are the unique lineages that are contributing to PD, and maybe those lineages one should be looking at more carefully, you know, try to prioritize those lineages maybe. So phylogenetics useful in both rating species and areas of conservation. So rating species would be, you know, when you identify those unique lineages that are boosting the PD. And then overall PD, which area has higher PD and all that. The main drawback is, you know, cost of sequencing. You know, ideally we should be doing this for all the species out there, you know. But fortunately, things are getting cheaper with every passing day, so that's okay. And then there are other issues with phylogenetics that we'll talk about tomorrow in terms of what genes to use and all that. And of course, you need some training when it comes to doing this kind of analysis. Yeah, so that was about PD. We have published a few papers on PD. Divya looked at 3 forest patches around Bangalore and found something really remarkable. Nandi, which has a really small patch, less number of species, has the highest phylogenetic diversity when compared to Devra and Durga and Savan Durga. These are the two other rocky outcrops around Bangalore. And we were wondering why is this the case. Turns out Nandi is pretty high. It's about 1,400 meters, right? And on top, you have a patch of evergreen forest, right? So that really pumped up the PD. And then we have also looked at the Western Ghats. Forests in the southern Western Ghats have very high PD compared to the north. So as you go from south to north, PD decreases. So forests in the south are more, you have species that are distantly related. So probably more sort of ancient lineages in the south. So anyway, so there are lots of other interesting work. So this is something you guys can take up.
How they calculated PD?
Which one?
Overall forest.
The same idea, same exact idea what I talked about. So for each forest, you know what species are found there. Make the list of all the species, right? So then you go on to the next forest, make a list and all that, and then you have a master list of all the species found in, you know, all the forests across, and then you build a huge phylogeny for all of them. For plants, you can go for genus level phylogeny, and there's a global phylogeny available for plants, for angiosperms, till genus level, right? So you make instead of species richness, you make a genus richness list for different areas. And then you come up with the master list of all the genera found in across all of your area. For that master list, you then extract the phylogeny from the global phylogeny.
You said that we should not include exotic plants.
Yeah, exotic plants should not be included.
Like in ridges or some area where there is so much invasive species are there.
Yeah.
In that case, we have to calculate because they have some abundance over there. How can we exclude them?
Because that is not telling you the actual native diversity, right?
they are having impact on that region.
They might be having an ecological impact. I completely agree with you on that. But you cannot use that as a measure of diversity at all, because it has been introduced from outside. You see?
We also exclude from species richness and other variables
Like what?
by calculating species richness
Huh.
or other indexes should be also excluded from those.
You mean like Shannon index and all that?
Yes.
Exclude what? I mean the exotics.
Invasive species.
Oh, invasive species. Yeah, definitely.
I have seen papers on phylogenetic diversity
Huh.
on invasive species.
See, again, that is a different question. That is a different question. That might be an interesting question in itself. Right? Are the invasives very distinctly related from each other, or you have closely related invasives coming in? Right? So you just make a list of invasives and figure out what is the phylogenetic diversity. And that might change from area to area, and you might ask yourself why. In some areas, the phylogenetic diversity for invasives is low, whereas in other areas it's very high. That itself is a very interesting question. Right? So it all depends on what question you're trying to address. Yeah? Yeah.
So if we theoretically consider two different habitats, and one is isolated, another one is connected, and both have in both the places we are taking the same area, and then if we compare, in the isolated area, phylogenetic diversity should be comparatively low, but the species evenness is usually higher, or density.
But we are not incorporating evenness here. You can incorporate evenness in phylogenetic diversity also, but in our case we haven't. But my intuition would be that a connected area would have more number of species simply because the extinction risk is lower there. Whereas in isolated area, there's a higher probability of extinction. Right? So the phylogenetic diversity in this case will be higher, the connected areas. So one has to be very careful while calculating this, exclude the invasives, and then I gave this talk in this workshop itself some 4 or 5 years ago, and there was a Sri Lankan group that had come. And the PI had also come, and he was very excited, and he told his student, yeah, we should do this work. So they went back, and she did this wonderful work where they compared 2 sanctuaries. Okay. Now what happened was, one sanctuary had a huge wetland. The other sanctuary is evergreen forest, but no wetland. So there were no wetland birds. Wetland birds boost up the phylogenetic diversity. Okay, so even though this other the sanctuary with the wetland was a very degraded forest, the phylogenetic diversity there was very high. So they should have not included the wetland birds, because now the comparisons are not appropriate. Either you compare 2 wetlands or you compare 2 forests. Right? And that goes for even regular diversity also. But if you look at the bird phylogeny, the waterfowls are like elephants. They are like long branch, right? So that really elevated the diversity. Yeah.
Is it a very good measure for assigning it as a sanctuary, or are there other measures?
Combination of phylogenetic diversity and species richness,
So they consider this first to assign it as a sanctuary?
No, that's what I said. One ideally use both species richness and phylogenetic diversity if there's the information on phylogenetic diversity. With the more sort of in many cases it becomes quite obvious. For example, if you have a isolated patch somewhere, say around Bangalore, okay, and there are many patches. One patch has loris in it, other patches don't. And in terms of species richness, otherwise it's all pretty much the same. So the loris patch will definitely have a very high phylogenetic diversity because of the loris, right? But that anyone will tell you. You don't have to do PD. Anyone will tell you, oh wow, this place has loris. It should be preserved, right?
I'm talking in terms of a butterfly garden in a big place where there is a invasive species like lantana, where there have been a lot of butterflies. So that will also be considered an artificially constructed place, right?
Yeah.
So how they don't include those? In a sense.
Can you elaborate on your question? I think you're onto something, but I'm not able to understand.
So it's a way of manipulating the PD to get the status of a wildlife sanctuary.
Oh, I see. Okay. I get your point. So you're saying that certain exotics might
Like
attract
those.
more distantly related native species,
Yeah.
thereby boosting the phylogenetic diversity. Yes, that could happen. Absolutely. And lantana is actually quite a good example, because even I think in our department, I don't know whose lab, Kavita's lab, they basically found that wherever there was lantana, there was high butterfly diversity and all native species. Yeah, so maybe one should then have a appropriate control where you look at the butterfly diversity in areas where there's absolutely no lantana and the local flowering plants are in high numbers, and see what the PD is in that area, right? And the two PDs then might be quite similar, but then one can argue that even though lantana is attracting all these butterflies, it's also having a huge impact on the other plants, or something to that effect. But yeah, that's an interesting point. Yeah.
And the other thing is that, like, we take different ecosystems
Yeah.
without any invasive species or any other anthropogenic trend.
Yeah.
So theoretically, phylogenetic diversity is constant, and if it raises, there is some issue, and if it goes completely down, there is some issue, right?
Oh, okay. I see where you're going with this. Yeah. So in this case, it might go up if there is invasives coming in.
Invasive or introduction.
Yeah, and going down with this habitat destruction.
Yes.
Yeah, absolutely. Yeah, so in a stable environment, condition, if you are monitoring PD over many years and then seeing what's happening, fluctuation there will tell you something about how the composition of species is changing. Yeah, that would be interesting too. Yeah, so you guys, you can definitely think of some projects here. Sorry, there was one more question.
How logical is to calculate PD for a definite group? I mean, if we consider only mammal, then species richness and PD, then how, or should we consider all species?
Yeah, absolutely. I completely agree. But you see, even when we are just taking species richness, what usually people look at: birds, mammals, maybe butterflies, reptiles and amphibians to a certain extent.
Insects also.
Insects, butterflies at the most. Insects is like so many, right? But it is usually birds and mammals. Every list will have when they are doing biodiversity assessment, right? So, but yeah, you're right. We should include as many groups as possible. And with plants also, it is mostly tree species, woody tree species. We don't include grasses and shrubs and herbs and all that. So there is definitely a bias towards certain groups. But yeah, we should try to include as many as possible. Yeah. So on that note, let me go on to applications of, because we still have time, so that we can spend more time on computer lab tomorrow. This might be a good time to even talk about other applications. Oh Lord, where is it? Oh, it's in day 5, yeah? Or is it day 3?
Should be day 5 or 2, because earlier it used to be day 4.
Okay.
So I stopped the recording.